Welcome to our second video on Chapter 6. We're going to pick up with covariance and correlation coefficient. I mentioned in an earlier video the advantages to investing in two assets that do not move in tandem. It's more helpful to the health of your portfolio to find securities that move opposite or somewhat opposite to one another, and covariance and correlation coefficient are the statistical tools we use to measure that. So I made some notes on this slide before I started recording to help you grasp what's going on here, save you a little bit of time. So we start off sort of like variance is the standard deviation. Covariance is the correlation coefficient, kind of. So because first you have to, in this case, calculate covariance. To get standard deviation, you have to first calculate variance. Here we start with covariance. And we take, you recall from one of the earlier slides, that the mean expected return for a stock fund, in these examples, these spreadsheet examples, was 10%. And that you may look back and see that when the condition was a severe recession, then the expected return was a loss of 37% right here. So in order to follow this process, we have to identify the deviation from the stock fund for each of these economic scenarios. And we'll do the same with the bond fund under these columns right here. So the math is we take the expected return under each economic condition. In this case, we're talking about severe recession. We expected 37% loss and subtract the mean return from that, and we get a negative 47% that we plug in up here. And then we do the same math for each of these conditions of the economy for both the stock and the bond fund. I think the mean return for the bond fund was 5%, while the stock fund mean return was 10. Then in order to get covariance, once we have these two columns that I highlighted in yellow, then we multiply the minus 4.7 times a minus 1.4, and you will get the product of those two columns. And then we multiply that by the probability of that condition of the economy. And we do that for each condition of the economy here in the column F. And then we sum those, and we get a minus 74.8. That is our covariance. We just calculated covariance. So pat yourself on the back. And then once we have covariance, we can calculate correlation coefficient, which is a more understandable number because correlation coefficient only goes from a -1 to a +1. So a -1 coefficient, correlation coefficient would look like this. That's perfect negative correlation. That would be a correlation coefficient of -1, okay? And if the two, you had two return histories that tracked perfectly, then that would be a +1. And a correlation coefficient of 0 means they do not track one another at all. They have no relationship to return histories, okay? In this case, we're comparing stocks to bonds. We could compare other asset classes and other things in any data set. Anyway, we take this negative 74.8, and then right here in this highlighted area here, you can see how you get correlation coefficient. You divide covariance by the standard deviation of stocks times the standard deviation of bonds. And I will drop our highlighting here and go back to spreadsheet 16.2, and you'll see the deviation of stocks here. The standard deviation of bonds is 8.27. And if you multiply those two values together, you will get the denominator in the equation I just showed you. So right here, our denominator is standard deviation, the stocks times standard deviation of bonds, and we divide that into the covariance, which is right here, and we get our correlation coefficient of a negative 0.49. So that is a fairly strongly, significantly, let's say significantly negatively correlated stock funds and bond funds there. So the textbook says that covariability changes slowly over time. Well, a problem that we saw in the 2008 financial meltdown was that all assets correlated. Everything correlated, everything went down. So while correlations and of course covariance may change slowly over time, we diversify and look at correlations in order to protect against negative events. And unfortunately, in the most severe negative event of the last few decades, correlations, everything correlated. So the very reason we designed portfolios the way we did kind of failed us. And so there's a lot of suspicion today of whether this methodology, which is traditional finance, really is sound. So sadly, but I think it's the best tool we have for building portfolios is to build those looking for low correlations among our assets. Around 1952, an economist named Harry Markowitz introduced something called modern portfolio theory, which is also known as mean variance analysis. He ended up winning a Nobel Prize for it. And we're going to look at that for a minute here. And one of the kind of rules, or here they call it a criterion, around mean variance, or MPT means modern portfolio theory, same thing as mean variance, is that if the expected return of A is greater than the expected return of B, and, this is an important and, standard deviation of A is less than B, that means A is less volatile, right? It's a smoother, doesn't have as many highs and lows, or as steep of highs and lows, or at least they don't, not as frequent. So if you have a low, and remember, volatility measured by standard deviation is a measure of risk, particularly in modern portfolio theory. So we're looking for lower standard deviation securities and portfolios. So if A has a lower standard deviation and its return is higher, then of course portfolio A would dominate portfolio B. We would have more of it well, let's say if those were two different securities, we'd use more of A than B. Another thing we need to do is identify what is our investment opportunity set. What are our opportunities? Well, here we start with a stock fund with an expected return or mean return of 10%, an expected mean return on a bond fund of 5%, and then we just experiment with different weightings. So here, now these columns A and B have to add to 1, right? So we start out on row 6 here with a short position in stocks of 20%. So then we have a 1.2 weighting of bonds. And we get to here, we're all bonds, no stocks, and so forth, until we have an all stock portfolio and no bonds. And then we calculate the expected return for each of those combinations, as well as the standard deviation. And you'll notice the standard deviations start high and get lower and lower, and then they begin to rise again. And if we look for the sweet spot, where do we have the lowest standard deviation? It looks like it's about here, right? There is our lowest standard deviation portfolio with an expected return of 5.5%. Now, remember we talked about the Sharpe ratio? We defined it as expected return minus the risk-free return divided by standard deviation. And that is so the Sharpe ratio gives us the kind of what's the term? Kind of a benefit to risk ratio, so that we can measure if it's worth the extra volatility by if we went up to a standard deviation of 20, we can get a higher return, but we can divide the 10.5 less the risk-free by the 20.75 and see which of these two that I have highlighted there have the highest Sharpe ratio. So when we plot those various combinations of stock funds versus bond funds, we end up with a curve like this blue one. And note that the y-axis is expected return, the x-axis is standard deviation. So at all possible combinations of standard deviation and expected return, they should fall on this blue line. And our lowest standard deviation or minimum variance portfolio is plotted right here, the left side of that curve. And you can see here is our stock, all stock, 100% stock portfolio. Here's a 100% bond portfolio. And of course, we would like to move north with this, right? We want to get a higher return, but you can see once we get beyond this minimum variance point right here, that our standard deviation begins to also get higher. So we have more volatility. And remember, when you take a 50% loss, say you have $10, you lose 50%, you're down to $5. Now you need 100% gain to get back to the 10. So low volatility or minimum variance is a good thing. You want to maintain all the cookies that you can, so you don't have to earn those super high returns to get back to even when you do have losses. By the way, I should mention that the book used a row of or a correlation coefficient here between bonds and stocks of 0.2, because that was the time of the writing of the book, the last 10 years, that was about the correlation, was a 0.2. Also, this blue line is known as the efficient frontier in finance parlance. So this chart gives you the efficient frontiers at different levels of correlation coefficient. The one we saw on the last slide was right here, was 0.2. And you can see here, if we had perfectly negative correlation of -1, then you would be looking at this line right here. So just kind of, and if we have a positive one, then I'm trying to tell whether that is, I think that would be this one right here. It's a blue line. Hard for me, yeah, I believe that's the one. So the optimal risky portfolio is the best combination of risky and safe assets. So what makes it the best? We're going to look at several criterion to sort of identify the best combination of those assets in a few minutes. Now we throw another item into the mix here, adding the potential for a risk-free asset. So you see right here at 3%, we're adding in, let's say, treasury bills that have a 0 standard deviation. And if we draw a straight line between that and our minimum, this is our minimum variance portfolio right here, that represents all combinations of minimum variance portfolio that we already looked at, combined with the third asset, the risk-free asset. You can also see that portfolio A here gets significantly more return right through when you come all the way over to the y-axis. It has significantly more return without much more standard deviation. So portfolio A likely has, it seems to have a higher Sharpe ratio, more return for the same standard deviation. Standard deviation is the denominator in the Sharpe ratio. So A looks like a pretty good choice. We draw the same straight line here from the risk-free. So this is called the capital allocation line for A, and it gives us all possible combinations of portfolio A with the risk-free asset. By definition, the optimal risky portfolio is the portfolio that generates the steepest capital allocation line. So we draw this line from the risk-free rate right here. So because we're mixing the risk-free asset with a portfolio, and at its steepest point of tangency, when it's tangent to the blue line, at the highest point, that is the optimal risky portfolio, and we're calling that portfolio O. And while portfolio O is the optimal risky portfolio, for a risk-averse investor that doesn't want this high level of risk, 10.15%, they can move down this capital allocation line to get the standard deviation to an area they're more comfortable with. And in this example, 5.58%. But at any point along this capital allocation line here is a good or optimal trade-off between the risk-free asset and the optimal portfolio. So in that last example, we ended up with 45% in T-bills, and the bond and stock allocation here was defined by the optimal portfolio. So we're going to stop here. I know this has gotten a little complex. I'm not going to ask you to make these calculations, but it forms a basis for, you need to learn these, understand some of these concepts because it's foundational as we move forward. So anyway, we will pick up the rest of this chapter 6 in the next video. And in the meantime, save money, build wealth, and invest. See you next time.